Movement in itself is a vast topic in statistics, and what we are going to do today is to understand the foundations, the very basics of movement, and we focus only of the order 2 so that we switch to expectation and try to solve a simple problem in expectation. So, what is moment exactly? It is the mean of the deviation of various orders. So when I say mean of the deviation of various orders, the order could be 0, 1, 2, n, or till r or s, whatever order that you can think of. The first four moments are typically very important in statistics, and let me give you this example of two different colors balls which are representing two different samples, and we'll try to understand what is the first order and second order moment from this. So here we have this is the axis, clear axis, and this is the origin, and we have 5 balls of red color and 5 balls of green colors at various distances from the origin. We'll come to the reason why we are talking of origin. So the first red ball is placed at 10, at unit 10 from origin, second is 16, 17, 18 and 24, and the green balls are at the distance of 16, 17 and 18 from origin. So if I have to calculate the average distance of these 5 red balls from the origin, then the way I will do is simple. We will do 10 minus 0 plus 16 minus 0 plus and so on 24 minus 0 divided by 5 balls, right? And that comes to be 17. That means the average distance of red balls is 17 from the origin. Similarly, for the green ones, which represent another sample, the average distance comes out to be 17, surprisingly, in this case also. Although we can very well see that there is a variation, there are variation in both the samples, but the variation in sample of red balls is more obvious. So, what is moment and how does it relate to this example? When we calculate the mean deviation from the origin of the first order means we are not squaring the deviation, the difference from the distance of the ball and origin. We are doing a simple plain arithmetic summation. That is the moment of the first order. And if we do the second order or the square of these deviations, then it comes to be a different value. Obviously the value will be different here, so let us say some other value, x, xy or xi or xj. So this is the moment of the second order. Well, let's come to this sample. So in both cases, the average distance from origin, as we have seen for the red ball and the green ball, is 17, and this is what we discussed as the moment of the first order moment about the origin. So here we are considering the reference point as the origin. So we are calculating the deviation from the origin. So we call it moment about the origin. So when we say moment about the origin, the standard syntax is we put apostrophe, or we call it dash. So mu1, let us say we call it dash or apostrophe or whatever appropriate you think to be referenced at. I will reference this as dash, so or complement or whatever. So this is not a complement, this is a syntax. So mu1 dash equal to summation of xi minus 0 by n, which is summation of xi by n 17, which we saw. And for mu2 dash, that's the second order moment about the origin, is the square of the deviation. So similarly, we can have these kind of moments of any order. It can be first order, second order, third order, fourth order, r order. Why these are important? These are statistically very important parameters which we will learn over the course. But first of all, let us focus on the second order. In this sample of the red and the green balls, we saw that the first order moment about the mean, about the origin, is same for both the samples. So we could not find any inference from the first order moment. So we go to the second order moment and try to see what is the difference. In the second order moment, we see that the second order moment about the origin for the red balls is 309, whereas for the green it is 289. So the variation in the red ball is more. So this is just a very simple example. And the second order moment, in this case, what we have calculated is about the origin. But what if we calculate about the mean of the sample? The mean is 17 here. So if we calculate about the mean, the deviation about the mean, or deviation from the mean. So moment is referred to as moment about the mean, and deviation is from the mean. So if we consider the deviation from the mean, and in effect we calculate the moment about the mean, that is called central moment, and which is referenced as mu1, mu2, mu3 without the apostrophe or without the dash that we pronounce it as. It's not the ideal pronouncement, but I use the term. So the second order about the mean, if you see here, the second order is, this is the equation for the second order, when we say xi minus mu1 dash or mu1 apostrophe. So this is the first order about the origin or the mean. So eventually you come to this equation, and here 17 is the mean we calculated, and then we calculate the second order about mean. Why it is important? Because this is also the variance. So expectation is linked to variance, we will see later on. So this is important to understand. So second order moment about mean, which is also known as second order central moment, is actually the variance. Similarly, and this is called centred. This is also called centred. Commonly, if you encounter this term in statistics, this is about the second order moment. Now the third and fourth we are skipping for the time being. The third is actually the third represents the skewness, and fourth represents kurtosis. We will not touch this, but and we are not even touching the degrees of freedom for the second order, third order, and fourth order moment. We will talk in subsequent lectures. But we will, from here, we will go to the other concepts in expectations. Right. So moments about mean of central moment, that is what we discussed. The zero order moment. So if there is a first order, there could be a zero order as well, right? So zero order is represented as mu zero, and this is a zero order moment about mean is 1. These are the standard values. First order will be 0 because xi minus x bar. So deviation, sum of the deviations about the mean will always be 0. So second order, so first order mean about first order or moment about mean will be 0, and second order will be the variance, as I said. These are important concepts, right? Now we know what is mu2, what is mu2 dash, what is mu1 dash. So mu2 is the moment about mean, second order moment about mean. Mu2 apostrophe or mu2 dash what I'm calling as is moment about origin, second order moment about origin, and mu1 dash is first order moment about origin. So there has to be a relation between these three. So the relation is this one, which is very important. This is very important. So the second order moment about mean is equal to second order moment about origin minus the square of first order moment about origin. This is important. This is important takeaway. So hence this is also equal to variance, as we have seen. So the variance of the distribution function or the random distribution function is equal to the mu2 dash minus mu1 dash whole square, or the moment about origin, second order moment about origin minus square of the first order moment about origin. A very important takeaway. Right. Now coming to the expectation part, we know that mu is equal to ex. E represents expectations, so we are not going into the problem solving examples here because there are multiple books that you can refer. We're just touching the basics of expectations and the moments till second order. So mu here is the mean. So the mean is actually the expected value of x, right? So if you have an observation, if you want to calculate expected value, so mu will be the mean will be the expected value of x. Similarly, mu r, or the moment r moment, will be expectation of x minus mu r, because we have seen why it should be. We have already handled this, right? So this we can also write as let me change the color. So this we can also write as expectation of this. Just we are substituting the value x minus mu is expectation of x, and this is r, right? So we can say that mu2, so instead of r we put 2 is equal to expectation of x minus mu to the power 2 equal to, just we are substituting x minus expectation of x square, which we know is equal to the variance. We already discussed this, right? So mu2 is equal to variance of x is equal to mu2 dash minus mu1 dash square. This is what we discussed in the previous slide, is equal to, what is the second order moment, this one, second order moment about the origin. So will be expectation of second order minus 0 square minus, and this is the first order, inside value is the first order, that's minus 0 the whole square. We're just substituting the values. These are plain mathematics. It's equal to x square, expectation of x square minus expectation of x, and this is whole square. So this is a very important takeaway. So let me change the color of this so that you will remember. So implies, what is mu2? Is variance, as we already said. So variance of x is equal to the expectation of x square minus expectation of x whole square. The second important takeaway of this, the first important takeaway was this one. Second important, the one highlighted in red. Second important takeaway is the one highlighted in red. And the third important takeaway in today's lecture is, if I have to calculate the variance of ax plus b, where a is a constant, it becomes a square variance of x. So the second constant will vanish. The proof you can yourself try, or you can refer any standard book and you will get this proof. So let x be a random variable, sigma standard deviation, and based on the formula that we derived in the previous slides, we have to find the expectation of z, where z is equal to x minus mu by sigma, and we have to also find the variance of z, expectation and variance based on the formula that we derived in the previous slides. Z here is x minus mu by sigma. This is a statistical term, is known as standard random variable. So this is the definition of standard random variable. So the problem is to find out the expectation of a standard random variable and the variance of the standard random variable. Right? This is the question. These are the takeaways that we had in our previous slides. Three important takeaways for variance. We will use this to solve this problem. So let us solve this problem. Let me change the color. So we have expectation of z. This is what we have to find out first, is equal to expectation of the standard random variable, which is z is expressed in terms of this x minus mu by sigma, is equal to, we take sigma 1 by sigma common. Let us take 1 by sigma common. This is x minus mu. Now we apply the third equation here. So not the third equation, this one more equation that I have to show you. Let me just show you that quickly. So if it is the expectation is expressed in terms of a constant into the variable, then the constant goes outside. So this is again one thing I did not tell you, but then yes, you can just remember this. Expectation of any constant k into x is equal to k into expectation of x. So I just omitted this, sorry, I did not tell you this. Anyway, so with this in mind, we can move this equation now to, will be equal to 1 by sigma expectation of x minus mu, right? And this can be now if you move expectation e inside, you expectation of x, and expectation of a constant is a constant itself, right? So this is mu again, and as you know, expectation of x is anyway mu or the mean, so it will be mu minus mu equal to 0. So what is it that we found out? We found out that the expectation of the standard random variable is 0. Okay, fine. Now we will use the other equations to solve the second part, the variance part. So we will solve the variance part. Okay, so what is the variance? How's that? Is equal to variance of, I can write like this, variance of x minus mu by sigma, the same expression, is equal to the variance of x by sigma minus mu by sigma, which is equal to, we can convert this in this format, 1 by sigma into x plus minus 1 by sigma into mu. Why do we need to do this? Because you see this equation, what we have derived, the variance of a into x plus v is a square px, v values, so this is a, so 1 by sigma is actually a, this represents v, so this will be a square into the variance of x, so 1 by sigma square into variance of x, right? And variance of x is the square of the standard deviation, so sigma square by sigma square, which becomes 1. So the variance of that standard random variable is equal to 1, and earlier we found out, then the expectation of the standard random variable is 0, where the standard random variable is x minus mu by sigma. So this is actually a very important concept in statistics going forward, and these are very fundamental things. I did not touch a lot of other concepts, lot of other equations, other theorems, multiplication theorem, addition theorem of variance and expectations, and so on. I purposefully omitted to make this video small, just to focus on these very small but important concepts. So thank you for watching, and I hope you like this video. Thank you.